Is voice clear? Voice is clear? There's an important announcement is there. First tell me voice clear. Then I will give information. That also you tell you heard clearly. No, if the voice is clear, tell me first. Audible? Okay. Simple information. I don't know, there is some power problem here today. I don't know why talking only it may go. From around 5 o'clock till now, every 15 minutes or 20 minutes, power will go for 10 minutes. I don't know why. As if they are playing. See, correctly you can see the watch also. Power will come, 10 minutes it will be there, then it will go. Then again, after 10 minutes further, again it will come. I almost typed here this problem and thought 7:30 there was no power. So I typed here and told leave it, tomorrow we'll have it. But now power came. So in case the problem comes once again now, see when I start now, if the power, same problem comes, if power goes off, I will simply close. I cannot play like that. 10 minutes class, 10 minutes power off. Clear now? No. In case it happens, I don't know when it will happen. Hope nothing will happen. So then same class will be tomorrow. I will start once again from beginning. If the class is held for around more than half an hour, okay, then that will be there, recording. But if the class is only 10-15 minutes, such a short class I do not want. I will restart once again tomorrow. My UPS has gone for servicing, that is the problem. Because not gone for service for 1 year, some problem is there. See, he took everything he took there, he will get it tomorrow only. Actually, as if they are doing it like playing only. As if by seeing a watch, 10 minutes over, take out the power. Okay, we hope that nothing will happen. Why I told? Because in case power goes off, then I will not wait for 10 minutes, again start, if it continues. If the trend continues, then no point in it, because if it is a Zoom class, okay, I can pause there. Here I can't pause. Okay, I'll start. See, make a note. Combined effect of axial force with biaxial bending moment. People solve sometimes axial load with biaxial bending. Both are same. See, column cross section subjected to axial load and biaxial bending moment, very popular. Same thing for footing. When you consider the footing, axial load will come and also bending will come this way. Sometimes people will call subjected to moment. Okay, but technically it is not moment, it is bending moment. Why? If a moment comes this way, reaction will come this way. See, together it is bending moment. So but usually people don't call bending moment. They simply use the term axial load with biaxial bending. Or simple language, whenever you consider the stress calculation, if you write M, it means always bending moment. It cannot be moment. Moment is rotational. So therefore, I will tell later. See, suppose there is a load acting here, eccentric load. You transfer here. It will create a moment. But that moment is balanced by one moment this way internally. So finally, it is bending moment. So clear now? So what happens is sometimes we may use the word moment. But even though I tell moment, it is always bending moment for the cross section. Clear this point? If I write M here for stress calculation, it is bending moment. I am telling why, because later some may comment, he is calling bending moment as moment. I will tell in the beginning only told. Okay, now, first make a note. This concept is very important for design of columns and design of footing. When you design the column, suppose RCC, see, we got one bending this way, one bending this way. If you remember, and axial force PU. If you remember, in RCC, you find PU by FCKBD. I will tell in the concluding class, I will explain this one. After this chapter is about to get over, this chapter is a very important chapter, so I decided to make public. Okay. Now, you get a term called PU by FCKBD. That I will call PU term. It will give you axial load by resistance. That factor will tell you what? Numerator is the action, denominator is the reaction or resistance. Then you write mu by FCKBD square. See, BD square. mu1, there I use the word mu1, mu2. I don't use xy. mu by FCKBD square. Once this way, once this way. If it is this way, you square this side. If it is this way, you square this side. All those concepts in RCC I told. But remember, at that time in RCC I told, the real concept you will get in strength of materials only. This basic concept will come in strength of materials. This is the time to correctly understand everything. Okay, then when you consider the footing, see there, axial load P. Sometimes people will tell, sir, 1.1 P. Ayo, that is 10% more. Then one moment this way, one moment this way. Then also you write what? P by A, you want only corner pressures, plus or minus M1 by Z1, plus or minus M2 by Z2. Then you that way you find the pressure. There you find the pressure. Column you find the stress. See, column section, if you apply axial load with the biaxial bending, you find stresses. Footing, when you apply axial load with biaxial bending on the soil, you calculate pressure. Pressure is also a stress only, but external. Okay, then you consider maximum pressure should not exceed SBC of soil, and we want minimum pressure not to be negative. Negative means actually not negative, should not be tensile, or there should be no lifting. These all came in RCC. The concept will come in strength of materials. Also for steel base plate, when you, I am giving introduction now. Steel base plate, when you apply the load with bending this way or this way, then one side it will compress the concrete. Because my base plate is resting on concrete. Other side, if the M is lesser, P is more, everywhere it will compress. That is the case of called what? The case where tension will not come. We use that word. Then, if M is predominant, one side lifting will come. RCC foundation, we do not want lifting. But steel, base plate, if lifting comes, no problem. Anybody can tell why? In steel structures, when you design base plate, if the lifting comes, no problem. Tell why no problem? Anybody can tell? Why no problem? Why no problem? Answer. If you know little steel. In steel, if lifting effect comes, there is no problem. Answer fast. At least I want, this is question I am asking so that I want confirmation that audio is continuously clear for you. Two reasons. One, to get reply from you. Second reason, just to confirm audio is audible fully. What I am talking is audible for you. Again, same thing. If you don't know, tell don't know. If you don't know, tell don't know. Kannadadalli, yaru sankocha padkobedi. English, don't feel bad. Tell don't know. What is there? If you tell don't know, that is not an issue. No reply. Then what? Otherwise, what happens? If reply will not come, I get doubt. When I get doubt, after some time, if there's a problem, I am wasting my energy talking here. See, I don't know. Okay, that is good. At least that is good means telling don't know is not good. Actually, you replied. Nothing to worry, because in steel you can provide anchor bolts. Now clear? You can provide anchor bolts. Anchor bolt will go deep inside the pedestal, and when lifting comes, anchor bolt will pull it down, and anchor bolt will not come out because of the friction or bond. So that length of anchor bolt you have to design so that sufficient frictional resistance is coming. Now clear? At least clear now? So there lifting is prevented by anchor bolts. So steel, no problem. But RCC, you cannot put anchor bolt. Why? If it lifts, see, suppose I am standing here. If I turn this way too much, see, I am getting lifted there. I cannot put anchor bolt there. I cannot put anchor bolt. Steel is not that way. You can prevent it by anchor bolt. See, suppose there is a bench. If you connect the bench bottom with the floor by nuts and bolt, even if you go to edge of the bench, when the lifting comes, it will be prevented. Okay, now, all these I will tell in the concluding part, when this chapter is over. Today is Wednesday. Today, tomorrow, day after tomorrow, 3 classes I require to completely clear this one. And if required, 1 more class. When I complete the strength of materials part, very briefly, I will connect it to RCC. Because strength of materials, I take axis XX and YY in the plan. YY is this way in the plan. Whereas in RCC and steel, I don't use XXYY because in RCC confusion. IS code wants major XX, minor YY. If the column is this way, IS code wants this is to be XX. If column is this way, if the column is this way, IS code wants this is XX. So to avoid the confusion, what I do? I take one axis as 1, 1, other axis as 2, 2. Sides I will take S1, S2. Here also same thing. One of the side S1, other S2. Structural B and structural D will come into picture now. Every concept correctly understand. Okay, now start. I will remove this one now. These all note you can write. Why this chapter is very, very important. Okay, now, first 1 minute. Let me see. Luckily, the power is kind on me today. I just put a small mark here. So that after writing, I do not want to go beyond that one. Just 1 minute. Oh, I am seeing how much is the lag. Oh, yes, now I went there. Okay, here. Up to here, no problem. I see the line there. Ah, yes, okay. I can go further more. Here. So that everything is crystal clear. See, you can see the screen better than Zoom now. Yes, see, screen is better than Zoom. Why screen is there? As usual, in YouTube, there is one advantage. What? You get a big screen. Okay. Start one by one concept. Now I will start now. By chance the power problem comes after I explain this concept, basic concept. Now see, almost 15 minutes over. Power has not gone. What you do is consider a member. See, consider a member subjected to axial force. Today we will restrict our study to compression. Tension not required. Actually, because why? In the case of columns or footing all, or when you consider column and footing, compression is predominant. So, consider a member subjected to axial compression, say P. See, remember, in strength of materials, there is no working load or factored load like that. We call the load P. In RCC, if it is working stress method, or in steel, if it is working stress method, we call P. In RCC, if it is limit state method, we call PU. In steel, even though limit state method, IS code told P. PD, they will use, not PD, PD is a strength. They will tell P, but they will tell that P is a factored load. That all you discuss in respective subject. So, in strength of materials, we don't consider working limit state method all. It is always what? Elastic theory. Consider, see, statements you are right. Consider a member of length L subjected to axial force P. This chapter I will do very systematically so that if you go through repeatedly, you get the complete control on the most important part of building design. Which one? Tell me. In the building, you are designing the beams, slabs, etc. See, nowadays, using software, beams, slabs can be designed very easily. There is not much chance of mistake. The dangerous part of building design, which one, tell me? Where you should be extra cautious. Something goes wrong, some wrong data or missing some data. One of them is column, other is what? One of them is column, other is. One of them is column, other is. One is column, other. Footing. When you consider column and footing, see, compression will come. But if heavy eccentricity is there or heavy BM comes this way or due to earthquake or wind load all, heavy bending can come. It is subjected to compression with bending. Say then, if it is RCC or steel, design principle is completely separate. You have to go for interaction diagram in RCC and some what you can call is series of equations in steel. If it is a footing, if it is axial force predominant, no problem. But when heavy moment this way or this way comes, especially due to earthquake all, then chance of lifting and over pressure. So the behavior of, or for that matter, a structural engineer's 90% weightage is for column and footing. That's why I am giving this much information for you. So therefore again, this class is not for those who just want some formula and then close it. Don't come to this class as usual. So this is not a column, a member subjected to axial force P. Now, this member can be quite small or quite big. Okay, this way, see. Big. End conditions all you won't bother. If member is quite small, then it will fail by crushing or direct compression will come. No chance of buckling. No buckling. No buckling. But if member is quite long, it is subject, there is a tendency to buckle. See, it can buckle. Then the cross section is subjected to axial force and also bending moment. Arrow mark I will explain later. Axial force, bending moment. See, for example, I will show you here. See, long means it is not only length, also cross section counts. Sometimes a member may be 10 meter long, still it can be a short column. A member, see, this member, very small length, it is a long member. Why? I'll show the reason now. See, first, consider a short member. See, for example, this one. See, if I apply axial force here, there is no chance of buckling, I am sure. Finally, it will crush. So, this is quite short. Short not in the sense only length, also cross section and material counts. This is over. Little later, we are going to column chapter. At that time, buckling you will consider. Right now, you believe me. Over. See. Now, consider a member which is quite long. Anywhere here? Long means it can be long based on length or based on what? Cross section or even based on material also. Or even based on material. See, I got a member here. Quite long. See, thin member. If I apply compression, see now, see, it will buckle. Now cross section is subjected to axial force with bending. If it buckles this way bending. If it buckles by chance this way bending. That all we'll discuss later. Now, come to this member, a small member. See, just now I took a wooden plank. You see, this is a short, but see now, this is a if this is steel or wood, this will be a very short member. But this is not that. See, by using two fingers, I will apply axial force. You know it. Section force cannot be applied by using one hand. You need both the hands. See. Or both the fingers. See, one finger here, one finger here. I will apply compression. See here. Can you see the buckling? Yes or no? Can you see the buckling? If it is steel, this will not buckle. If it is timber, it will not buckle. But because this material is not plastic, what you call, I don't know. What is the name for this material? That, see, this is a, thermocol like that. It is very weak. See, you can see compression means buckling will come. See. Okay, leave it. Clear now? There will be buckling. This is playing with me actually. 1 minute. I lost control of the class only here. 1 minute. Okay, now I got control back. Okay, now I will not put in the pocket, because when I put in the pocket, because of that side touching, it will vanish. There's got problem. I put here now. Okay. See, now our study is meant only for short column. Very important. Short column. Now, so therefore, our study is not short column, short member, time being. Short member. Make a note. Somebody may tell, see, foundation, when you consider, it's a short. Why? Because huge cross section, length is always in direction of force. There is no length much here. See, when you take the foundation this way, when you apply load on soil, what buckling will come? Which will buckle? Soil cannot buckle. And columns can buckle. Nothing to worry. If the buckling comes, then you apply corrections. See? If long, only for column, possible only for columns, RCC or steel, not possible for footing. When you consider footing, see, load is this way, this is the length, this way is the length. It is very, very short. First of all, see, you see here, how you can talk about buckling. See, suppose there is a footing slab here. Apply a load. What buckling? What? This is the length. What buckling there? So footing slab, buckling will not come. But column, buckling will come. When in the strength of materials, you study no buckling if it comes separately in column chapter later. Pi square EI by L square, L effective square by Euler's formula, or some crushing stress into area by 1 plus alpha into lambda square, Rankine's formula, other formulas you study there. So, if long, only for column, there will be correction. There will be correction. Correction to the short column theory. See, in RCC, what you do is, you calculate PU by FCK BD. That is for a short member. If long, you calculate L effective by lateral dimension. That ratio, if it comes more than 12, column is said to be long, it is weaker, buckling chance is there, then you consider additional bending moment given by PU into the side divided by 2000 into L effective by B whole square. If you remember RCC. Or in steel, you calculate L by RXX, L by RYY, that way accordingly you consider the strength in axial load you can apply based on this way buckling, based on this way buckling. You apply corrections there. That is somewhat interaction formula. But strength of materials, basic study, always done for short member. Short. So remember, if long, if buckling chance is there, it will be considered in the design field. In the design, there will be correction. Okay, now therefore, now consider a short member. See, short. If I take the cross section here, I don't know, see, this member is maybe, this member actually is like this, imagine. This all technical portion, understand. If you apply compression here, this is the cross section. Any cross section, it can be rectangle or I section, anything. For basic theory, I will take rectangle, but I will not use property of rectangle. If it is I section, you can make out slowly. I will not use any property of rectangle. Okay, now this way. This cross-sectional area is A. Cross-sectional area equal to A. So, if the load is axial, then everywhere there will be axial compressive stress. Axial compressive stress. that is sigma in compression equal to P by A, force divided by area, uniform across the cross section. One small doubt I asked somebody. Someone wrote the sketch like this. I won't tell the answer. He was showing axial load here. Then I asked a question. See, you apply axial load here. It is acting through a small point. So contact area is so small, how you can take stress equal to P by entire area? He told, no. There will be dispersion. Agreed. See, even if you apply axial force, there will be dispersion. I will tell you now. Show it now. See, these all points. Do you want to understand, want to know or not? Tell me. If you do not want, tell me, I got equation. Do you want to understand all these concepts or no? No means tell me, I will go to equation. What is there for me? I will save the time. Do you want to understand all these concepts? Every finer concept of column and footing means now is the time. Otherwise tell me, I can go to equation. Why waste time? Oh, luckily see, there is no power problem. This class is for concept only. See, even though in the thumbnail I wrote combined effect of etc. class 1. If you see title, it is BSK class, basic structural knowledge class. Class is meant to my BSK batch. Those who want to learn the concept. Others can utilize it, that's all. They have no claim that you are explaining too much. Then don't come to the class. Who told you to come? Sometimes I will be harsh only. Did I ask you to come? No. You cannot comment that you are giving too much explanation. Yes, I am doing in YouTube because let it be universal. Because recently there is not much activity. So I thought at least some activity in YouTube is required to keep in touch. Now see, I will apply an axial force here. See, point. I will do one thing now to understand more clearly. I will show you something else. These all you are right. See, I will put my hand here, place a book. See, my hand is spread. I will apply a force here. See, force is through a point. But when you reach here, are you feeling the force only at a point or spread along the entire area? Tell the answer. See, if I apply a force here, are you feeling the effect only for that contact point means somewhere here or across the full hand? Tell the answer. You take a book or further, you take some member this way. Put in the hand here. Put in the hand. Apply a point load here. Tell me, where it touches your hand, are you feeling the effect, pressure, only through a point or spread for cross section? Answer. Entire area. Because when you apply the load, there will be dispersion. Therefore, after some distance, when you apply a force here, right now it is through a point. But after traveling some distances, then it will, dispersion is there, it will spread for entire cross section. Clear or not clear? So therefore, we take P by A, force pi. See, axial stress is always force divided by area. That all I can't tell. Why? This is a BSK class. I already told you 1,000 times earlier. That is clear? P by A. Okay, now, someone, I asked a doubt. See, you apply a force here. How you can take area? Stress will be infinity. If the area is very, very small, stress will be infinity. Then he told, I don't want to tell who, dispersion is there. Okay, dispersion is there after some time. Dispersion is there after some time. See, after some distance, then dispersion will come. What about here? It will be infinity. If the area is very small, see, if you apply a force of some heavy force, very small contact area. Then he told, no, that I don't know. Then you ask so many things. I told him then immediately, see, in pre-stressed concrete, If you remember pre-stress concrete, when you apply the axial compression, in the end some portion, tell me here stress distribution is highly complicated. Why? There is no particular equation. Anybody can tell me if the beam is very huge. See, suppose the PSC beam is like this, not much length. Then in the end some portion, what is the name given for the end portion of PSC beam? Anybody can tell? There's a name for that one. See, these are all finer concepts. What is the name given for end portion of PSC beam where pre-stressing force is transferred to beam for some length? Then they will tell from here onwards it will be like this. See, it will be like this. So here it will get dispersed here. So this region needs special attention because here load is actually a point load. Anybody can tell what is the name given in PSC for the end portion? First, you heard of it in syllabus. There's a name for that one. Magnell's theory, then so many theories are there. And some special reinforcements are there. And it is called anchorage zone stresses. If you don't know, tell don't know. I will tell the answer. If you don't know, tell don't know. I will tell the answer. In the end portion, what is the name given for that one? One of the answer. Either answer or don't know. No reply. Either answer or don't know. So that I want confirmation that what audio problem is not there. Two reasons. I ask question once in a while only to confirm that audio problem is not there, and also to see that you are interested in this one. Fast. Comment. Either tell the answer or don't know. In future when I ask a question, you no sir, okay, leave it. What no? I told you in the class, okay, leave it. It is called end block. Heard of it one? End block, where you calculate bursting forces. Remember, you calculate bursting forces, FBST, in pre-stress concrete. But usually, people who study PSC, they don't go to this chapter. Why? Complications. They study stress part, deflection part, loss of pre-stress, and shear, and then ultimate MR. 5 questions will come. So many people in the college also, they don't do this one. Sometimes even when I take PSC class here, time problem comes, I will tell complication. Sir, bitbudi, not required. See, already how many questions over? 6, 7 questions over. Sir, then leave it, sir. So, it is called end block. You go to your B syllabus, open PSC. There, see the syllabus. You can see stress analysis, deflection, shear, ultimate load, flexural strength, and then you can see end block. See there? You can see end block there. See now, today only see there. Or open a PSC book. See how much complication is there for end block. Now, then I ask the question. Okay, now tell me. In a column, if you apply load this way, same end block theory required here also. Then the answer came to me. Yes, but I don't know. Please tell the answer. I will tell you the answer. In the column, you are not applying point load. Who is applying point load for a column? See, who is applying point load for a column? Actually, in the column, see, a beam will rest here. When the beam rests here, is the applied on the column is point load or distributed? Tell the answer. The simple question. Imagine a RC column over which beam is resting. When the beam load is transferred, is it transferred to a point or spread along the cross section? Tell the answer no. Is it point load or spread along the cross section? It is distributed. So, even if you see this question, so many will not answer. Actually, load is like this only. Listen only that for simplicity, what you do? In the thumbnail, I wrote this way. P. This P is what? Total load transferred. Now clear? So that's why there is no end block theory in RCC or steel. RCC or steel case, ordinary case, there is no end block theory. Why? See, load is spread there only. But in PSC, not that way. PSC, in the post tensioning, when you tension and anchor, see, load is transferred through a point or small area. There is the anchorage plate. Then there will be dispersion. Therefore, only in PSC we consider end block effect or that dispersion of the load, that is called anchorage zone stresses. Clear now? That is called anchorage zone stresses. Okay, now leave it. So in future, remember, if I write a column section and show you axial load P this way, means don't tell it's a point load, it is the resultant load due to all this load, combined load is P. Clear now? The combined load is P. And one more thing, in case of footing slab, no, see, column contact area is small, therefore their distribution is there, dispersion is there. Their dispersion is there. In footing slab, dispersion is there. See the ES code? That load transfer formula is there in RCC. For footing slab, it is there. Okay, leave it now. So now onwards, if I show arrow mark, it is actually resultant load. Okay, stress equal to P by A, compression. Okay, now. Or if you draw the stress distribution diagram across cross section, it is a rectangle. I will put plus here because in this chapter I am taking compression positive. See, in principal stress chapter you take tension positive, but in column theory you take compression positive because our stress is always compression. So compression positive, but in E tab it is tension positive. That's why in the class I told in RCC, in footing for manual design in the class, pressure should not come negative, but in E tab, pressure should not come positive. Why? We want compression, no tension. In manual calculation, compression is positive. So negative means tension, should not come. E tab, tension positive. There, we do not want tension. So there, it should be always negative. Okay, compression positive. What is the answer here? From here to here, or anywhere in the cross section. See, for the entire cross section, wherever you see stress equal to P by A and P by A. Compression. Compression positive. This clear? If the load is axial, it is plus P by A everywhere. Fast. That is pure axial load. Okay, now consider the case of, see, now do one thing, instead of horizontal member, you consider a vertical member. Why? Because our theory, our study is for columns and footing. See now, consider a vertical member here. See, vertical member subjected to axial compression P. Length is quite small so that buckling is not considered. Or if I put a 3D sketch here, if I put 3D sketch, show rectangle, no problem. This is the column. I will do one thing now. See, since length is not required, I will show cut. Okay, now, see, load is actually, strictly speaking, load is spread, see, this way. Now, because of that one, axial force is P passing to CG. If the line of action of the force coincides with longitudinal centroidal axis of the member, it is called axial load. Or when you consider cross section, see, if I take cross section here, rectangle, anything, then I cannot show the load. It should pass through CG of the cross. Load is perpendicular. Here I can show, here I can't show. Load is this way. So if the load passes through resultant load, see, even if the load is spread, if the resultant load passes to CG of the cross section, it is called axial force. axial force or axial load. Axial load. Then what? For entire cross section, everywhere, stress sigma equal to plus P by A, because compression, or you can tell stress equal to P by A compression, or with sign convention, compression positive, it is plus P by A. Uniform throughout, uniform everywhere. This should be clear. I am not asking clear or not. Now consider the case of column subjected to axial force with bending. See, that is not only P, bending moment M will come. Now, it can be only with respect to one axis or both the axes. See, when you use the term P, you have to tell always the word along. When you explain the bending moment, you should always use the word not along. Anybody can tell? When this I told you yesterday. See, somebody say, you come to YouTube. He told yesterday the class is not there. You believe what I tell. Every class is not for you. You believe what I tell. Those who are coming, I told you, when you consider bending moment, you should not consider the word along. I told you what word to be considered. For bending moment, what word to be considered? No along. Along is wrong. For force, axial force or shear force, you can use the word along. For bending moment or even moment, the word is not along. Tell what is the word? The word is not along. What is the word? It is about. About what? It is always about an axis. About an axis. And when you consider moment, it is moment about an axis. See, I told you, if moment is this way, this is the axis. If moment is this way, this is the axis. If moment is this way, this is the axis. This I told you yesterday. For newcomers, once again I will tell you, see, if moment is this way, this is the axis. If moment is this way, this is the axis. Or if moment is like this is the axis. Definition: a body is said to be rotating about an axis if each and every point in the body remains at constant distance from that axis throughout rotation. See, when your vehicle wheel is going this way, it is rotating about that axle here. See, that axle rotation, you see, if it rotates this way from this axis, it is a constant distance, radial distance. Further I will not tell. I made fully clear yesterday for you. Newcomers, believe me. Over. So M is always about. Now, about, when you use the word moment, it is moment about the axis. But remember, when you use the term bending moment, then, see, when you use moment, when the term moment is used, it is always about an axis. An axis. But when you use the term bending moment, then also it is about an axis only. About an axis in cross section. I will tell once again, in case of bending theory, it is axis should be in the cross section if you want to define the bending moment. Okay, now, and write yourself, then that axis in the cross section about which you are considering bending moment, that axis is also called, first, that axis, I will not repeat again and again now. Newcomer should understand that axis is also called, first. Yesterday I concluded that one. I concluded when moment is there about an axis, but when it is bending moment, then that axis should be in the plane of the cross section. Only for twisting moment, axis is perpendicular to the plane of cross section. For bending moment, axis should be in the plane of the cross section, and then that axis is called, name first. Till you answer, I will not go further. I will wait for 10 minutes and stop the class. Why? Those who are here, I told yesterday, concluded. This you can't tell, don't know. That axis is called, first, I will count 10 and then stop the class if you don't answer. 1, 2, I am going to end the class then. 3, 4, 5, 6, 7, 8, 9, 9.1, 9.2, because I don't want to stop the class. 9.3, 9.9, 9.91, 9.92. Finally answer came. Thank you. Very kind of you. It is called neutral axis. I will not repeat again and again. That axis in the, see right here, that axis in the cross section about which you consider bending moment, not moment, bending moment, that is called neutral axis. Okay, thank you. Very kind of you. Actually, I got confused. I was not knowing the answer. So thank you for giving the answer. Now see how the bending moment can come for the cross section. See how BM will come for cross section. I told repeatedly, so many people are using bending moment for the beam. What beam? Bending moment is for cross section. It is external, resistance is internal. One fine day people will change their idea. 99% people all online, they will tell bending moment is internal. Wait for some time now. Tell me internal or external. Wait for some time. Okay, start. It can come in two different ways. Tell me. First way. Directly bending moment for cross section. I will show it here now. See, it can come. You write here first. Directly bending moment for the cross section. See, you should write all these notes. For example, see, this is a column. This is a beam. These all, those who are serious should write everything, including a model. Where is the one more wooden plank? I had one more wooden plank here. I think I threw it here. See, imagine a column and a beam. If the beam is simply resting, it is called simply supported. But if it is monolithic construction, see, then this is not called simple support. It is called rigid joint. See, this is the beam, this is the column. If it is like this, it is called simple support, where only vertical reaction will come here, and for the beam here, bending moment equal to 0, unless there's a couple applied there. Okay, but usually we get in RCC beam and column monolithic. See, monolithic. The bars will come this way, these bars will go here, this will continue. Okay, leave it now. Monolithic sufficient. It is monolithic. Then this is, if I put a sketch here this way, suppose you take a frame. Imagine frame is like this. Or see, imagine this is the beam and column, simple arrangement. Okay, now suppose I put a line diagram. It is like this. Base you can take fixed. Then when there is a loading here, then this member will sag here. But here it will hog. Or there will be end moment for the beam. Because it is rigid joint. Whatever end moment for the beam, if the end moment for the beam is like this, suppose I call this is MB and MC, ABCD. Then This MB and MC are reacting moments. Beam is supported by column. Therefore, when the beam is supported by column, see rigid joint. See the bending now. I will show you. It is not simple. Ordinary beam will bend, simply support beam. When rigid joint is there, see now what I am doing. Here, there will be reacting moment. That's why in all multi-story building frames, see there, tell me, yes or no? In case of beams in the frame in RCC, you provide top steel here, bottom steel here. Why? This is here sagging beam, tension at the bottom, here hogging beam, tension at the top. Tell me yes or no? This is the AST for midspan section, this is the AST for support section. Clear or not? They will be hogging beam. Tell me yes or no? They will be hogging beam. No answer. Luckily, power, there is no problem. Tomorrow I will get the UPS, nothing to worry. Hope he will give tomorrow. Or power problem every day will not be there. Clear? So support will hog. Yes. Therefore, this reacting moment will hog. That reacting moment is reacting moment for the beam from the column. Why? Supported. So if you reverse it, what will happen? Whatever this MB, if you reverse it, it will become effect transfer to column. MBMC. So then why this you know in strength of materials earlier. Action and reaction. If you reverse the reaction, you get the action on supporting member. So if, see for example, for the beam, there will be upward reaction. Reverse it. You get downward load for the column. Moments are this way for the beam. Means this way, moment is for the column. Now, therefore, now if you see column cross section here, if I put this way, see, if I put some column cross section this way, 3D view, it is subjected to axial load P along with the bending moment M. See? Now there will be axial load and bending effect. Now, it can be not only this way, it can be this way also. See, if you consider this way frame action, then there will be one more moment this way. See, this way. So, this will give what? Axial load with bending. That is directly bending moment because of rigid joint effect. That is one case. Tell me the second case. I told one is direct answer. Now, not direct, not indirect. Second one is when the P is eccentric. When P is eccentric, that is, imagine column section is here. This is a column section. Okay, I'll put the lengthy one here to understand. This is a column section here. Now, this is the CG. See, these are the axes in the cross section. Instead of load acting here, suppose the load is acting somewhere here. P. That is called eccentric load. Line of action of P will not pass through CG of the column. So, this is called, whatever is this distance is called eccentricity E in this direction. Later I will tell you one of them EX, other EY. Okay, now, in that case, you can do one thing. If you remember correctly, an eccentric load can be replaced by, you can replace this eccentric load here by an axial force P along with the moment M equal to P into E. Know it? Replacement theory. See, you know in steel structures, bracket correction, all will tell, yes sir, yes sir. Why? Because examination, if it is P, if the bolts are here, this all will happen. Sir, clear sir. Okay, P. Then you write force P, moment M equal to P into S sir. Because of that question I passed steel. Why? Sometime 20 marks question. They will tell, yes sir, correct. So you can replace this force, the effective transfer here. It will be, this will force P here, will create a moment like this. So it will be equal this way. This is called, now this becomes bending moment for cross section because of load is eccentric. Clear? Bending moment for cross section because load is eccentric. This is very important principle today. I don't know whether clear or not. That clear is old clear, I think. You just tell clear so that I can continue. I want to know that everything is clear now or audible. Oh, I am in 144p. That's why blurring. If I go to 480, clear. Okay, now somebody will ask the question, sir, how the load can be eccentric? Yes, load can be eccentric because of the reason, because, see, sometime I will tell you, you write yourself, this is the column. If the beam runs this way, then beam will press the column like this. First of all, pressure is not uniform, that you ignore. Okay, then you can tell practically, if the beam is resting like this, you can tell, if the member is continuously running, you can tell axial load. But if the beam stops here, see, simply support beam, then when you apply the load here, see, due to bending, remember, when the transfer is done for column, it will not be uniform transfer. On the inner side, pressure, what? The pressing effect is more. Outer side, see, when the beam bends this way, there will be slight lifting here. Therefore, see, because of the slope, pressure will be little more on inner side. So resultant load will slightly shift this side. But people usually ignore it. But best example is, imagine a column here, a beam running this way. See, this column, you make a note, 200 by 600 column. Beam, 200 by something, say 500. If the beam rests this way, no problem. Why? You can practically, people will tell axial load. But if the beam runs this way, exactly to center of the column, again you can tell axial. Strictly speaking, not possible, okay. But so many times what happens is, for some reason, this beam will come here. See, the beam will rest here. Practically, have you seen or not? In a long column side, longer side of the column, beam is not placed at center, it is placed at the edges because of architectural problems. The beam will be somewhere here, this way. Have you seen or not? See, have you seen or not? This way. That is, if I put 3D view of the column, the beam will rest here. Here. Have you seen practically? If you have seen practical drawing, so many places you have seen that one. In your house only it is there. In your house only you can see it. Suppose there is a column of 200 by 500 column. Lengthwise column beam will fit to width of the beam. The beam going other way may not be through center. They want at the edge. Little lag. Now, voice clear now? Okay. Therefore, in such cases, what will happen? The load, beam load, when you transfer to column, will be transferred here. See, contact area is here. So, with respect to column, it becomes eccentric. See here only. If the column is this way, if the beam is this way, no problem. Axial load you can tell. If it is exact to center, axial load. But no, what they want is, they want no offset here. See, beam will rest here. If the beam rests here, the beam load, when you transfer to column, it will be transferred here. So with respect to CG of the column, it will create a moment. This is this way moment possible. That is, so therefore, one option is directly BM because of the frame action. Second one is due to when P is eccentric. eccentric may be about one axis or both the axis. See, once again, if the column cross section is this way, see, if the cross section is this way, for example, these are the axis, CG axis. Okay. If the load is acting here, then this is the eccentricity. Then the effect will be, this all we will discuss tomorrow. This everything we are discussing tomorrow. Then you can shift it here with the load P and moment like this equal to M equal to PE. Or suppose there is a column cross section. See here. Yes. Column cross section where load is somewhere here. Then this will become E. Then for the cross, these all your, those who are serious should write all of this one. Then for the column cross section, when you shift here, it will become axial load P and a moment P, this will come this way, M equal to PE. Therefore, these are called as, you call axial load with the uniaxial bending moment. Clear? These are called axial load with the uniaxial bending moment. Clear or not? Further I will not explain why. You know this one. These are the case of, one is eccentricity along this line and this axis. Other is eccentricity along this line. So this is the case of axial load with the uniaxial bending moment, or eccentricity is, see, this axial load with uniaxial bending, or you can tell eccentricity is only with respect to one of the axis. Here, eccentricity is only about this axis, see, because load lies in this axis. Here, load lies in this axis. Eccentricity is from this axis. Here, from this axis. This is a case of axial load with the uniaxial bending, where eccentricity is only with respect to one of the axes. But sometimes, see, our study will be biaxial, or second case is eccentricity with respect to both the axes. See, now, suppose the cross section is here. Okay, start. This is one of the axis. Tomorrow it will become red color. If the load is acting here, see, then this is eccentricity. If I call this as YY axis, this is XX axis. This is eccentricity along X axis. Whereas, see, this is, I can show here, this is eccentricity with respect from YY axis. Now if you replace, this all will discuss tomorrow once again. All this will discuss tomorrow once again. Now if you replace, see, you shift it here. See, from here, when you shift here, it becomes axial load P, then it will become axial load P, and then see, P into EX is this way. One moment will come this way, that is P into EX. This is XX axis, this is YY axis. P into EX is not BM about X axis. P into EX is BM about Y axis. Tomorrow fully clear, TFC. This tomorrow I will make fully clear. And again see here, because of this way, one more moment will come this way. That is P into EY. P into EY is force into eccentricity along Y, is not BM about YY. It is BM about X axis. That is why tomorrow your formula will become sigma resultant equal to plus P by A plus or minus mx by ix into x. See, not x, mx by ix into y plus my by iy into x. P by, tomorrow it will come, P by A positive, then plus or minus mx by ixx into y, my by iyy into x. If you know a method called column analogy method, heard of it? There, after drawing bending moment diagram concerning a load, after you draw analogous column cross section, you find mi by the formula P by A plus or minus mx by ix into y plus my by iyy into x. That will give you the pressure, induced pressure. Then ms minus mi will give bending moment. That is analysis of indeterminate structure given by Hardy Cross. A beautiful method. But nowadays, completely removed from syllabus. It gives you very fast solution for gable frame. Portal frame, nobody wants it. Why? Other methods. Gable frame, very popular, called, or for non-prismatic members, very useful, called column analogy method. Nowadays, because of software all, nobody wants that one. Ayyo, so what? Software will give in seconds. Why you want to do all those things? That's why syllabus removed. Heard of? Called column analogy method. Okay. Now, therefore, remember now, I'll just put the, luckily see, put the final part today. Now see, consider cross section of column. Consider cross section of column. Column. I will show rectangle, no problem. See, I will show rectangle today. Remember now, now I am not writing 3D. See, one more thing. See, one more thing is here. See, if it is this way, if you put somewhat 3D, you can show load P. Moment is like this. You can show 1m here. You can show 1m here. But when you write the plan, you cannot show it. Why? See, I will put the cross section here. Cross section. Anything. Or this side. Okay, consider cross section. Okay. See, because when you study, you consider only cross section. This is a column cross section. Now see, load is perpendicular. You cannot show it through axis you mark here. I show red color. These are the axes. Rectangle, it is valid for, I am not using any rectangle property here. But symmetry is required. Okay, here, CG. Load you cannot show. It is like this, P. Here also, load is this way, P. Here also, load is P. Here also, load is P. This is only axial force. Only axial force. P, perpendicular. Here, these are axial force with uniaxial bending moment. See, P with this way, actually not that way. You cannot show it. It is actually, see, this way. In the plan you cannot show, but what actually you have to write like this. This way if I write, how you can see it? So, usually I write like this. Okay, this way. Or show dotted line today. Today dotted line, next time solid line. Okay, this is suppose tell xx axis, this is yy axis, this also xx and yy, xx and yy in the class. When I go to column and footing later, I will call 1, 1 and 2, 2. I will tell the reason later. So, this is P with m about y. I will tell you why it is m about y, not mx. This clarification will be tomorrow's class in detail, mx. Or P with, see, my. That is load with this bending moment or load with this bend. It can be, see, it can be this way or this way. Tomorrow we'll discuss. It can be this way or this way. That is not a problem. Or this is See, if for this one, this is the axis. This all I will explain. And last case, this is what? These both are, this will happen when load is either directly BM comes, or this will happen when load is eccentric along XX. Load is eccentric along XX means eccentricity is about YY. Here, load is eccentric along YY. Load is eccentric along YY means it is what? It is, this is not MY, this is MX. Ayo, see, I can make out. Load is eccentric along YY means it is eccentric about XX. Nothing to worry. I will make everything clear. One of that one. Here only P, uniaxial, or it can be My and Mx. This is axial force with biaxial BM. Tell me, this much concept, if it is fully clear, new I will not start and not take any break today also. Luckily, thanks for the KEB or BWSSB, it was from 5 o'clock, every 15-20 minutes, it will come and go. I got so frustrated. 7:30 when I came here, power went off. Then I started typing in the message box. There is a problem for power, so it is playing with me every 10 minutes or 15-20 minutes. It goes and comes for 10 minutes. So it will spoil the class. So better we'll have class tomorrow. I was about to type. Before sending, suddenly power came. Then at 7:35 power came. Then I decided, okay, take a chance. See, today, if I cancel the class, I would have felt very bad. Why? No problem. Sometimes it happens. It is actually frightening me. After a long time, I'm coming back to YouTube now. So anyway, luckily, thanks for BWSSB. No, sorry, not BWSSB, BSCOM. Confusion, what to do. BSCOM in Bangalore, or earlier called KEB. Okay. Now, is this concept completely clear? Tomorrow we will study correctly effect of P, effect of My, or effect of Mx, and then how to combine the stresses and all the concept. Tomorrow will be fully mathematical. If this much is fully clear, tomorrow I will continue, because why? Still 5 minutes I can't do anything. I can start something, but time problem will come. Okay, leave it now. I will most probably tomorrow, before the class, some sketches I will write, not for practice purpose, to save the time. Okay, we will meet tomorrow, same 7:30. This class, today, tomorrow, day of tomorrow, Friday, and if required on Tuesday, over. Then again your class will continue in Zoom only. Only this particular chapter, combined effect of P with Mx, My will be in YouTube class. Okay, thank you. We will meet tomorrow. Go through today's class thoroughly and understand everything. So many principles I told. Go through everything and thoroughly understand. Once these concepts are clear, see the grip you will get later in structural engineering. Okay, thank you. Always attend live. All those who came today, come tomorrow also. Those who are doing recording, come live. Then only you understand. Then only you make the mistake, you comment and chat with me. Then only you make the mistake and I correct it. Okay. This I am telling from beginning. I know the response. Okay. Thank God for the power problem.